If we haven't met, my name is Angelo Ricarte. I'm a postdoc at the Black Hole Initiative. I've spent time studying black holes both on galaxy and cosmological scales, as well as event horizon scales. And today I'll be telling you about insights zoomed in on the smallest scales from the Event Horizon Telescope and GRMHD simulations that can inform us about black hole activity, where all of the action happens. So I've spent a lot of time in the past few years studying the Event Horizon Telescope. I've been very involved in writing the theory paper since 2020, so I'd be happy to take any questions about this work as well. But there are two main points that I wanted to bring up in this meeting. First of all, we've confirmed that the accretion rate onto these black holes is orders of magnitude suppressed relative to Bondi. And we've seen several talks in the past couple of days trying to explain this. And then second, both of these images favor what we like to call magnetically arrested disks, or MADS, in which the magnetic field strength on the horizon of the black hole has saturated. In these cases, the magnetic fields become dynamically important, transforming the disk dynamics via magnetic pressure and tension. This is in contrast to what we often call standard and normal evolution, or SANE models, in which the magnetic fields simply go with the flow. Those are my favorite acronyms in all of astronomy, as tortured as they are. In addition, these models produce natural explanations for multi-wavelength flares. If you were watching the movie earlier, you would sometimes see this cavity appear in the millimeter image that I'm simulating here. And this is due to what's called a magnetic flux eruption event, where as more magnetic flux is trying to accumulate onto the black hole, reconnection occurs, causing an expulsion, which could also power high energy flares. In these models, we have studied the feedback properties, and we have known for over 10 years that such magnetically arrested disks launch very efficient jets, and that these jets are powered by the Blandford-Znaick mechanism. As we look at this equation on the right, you could see that the jet efficiency, that is the power per rest mass energy accreted, scales, at least for low values of spin, with the square of the spin as well as the square of the normalized magnetic flux on the horizon. And so if one were to maximize both of these, maximize the flux by making it magnetically arrested, and then maximize the spin by bringing it near unity, you can actually get jets that are over 100% efficient. And this is a plot from Narayan et al., 2022, where we were studying spin evolution in detail. This result was also seen before, Tchaikovsky et al., 2010. The way that this is possible is because the jets are extracting spin energy from the black hole. Of course, that would be completely impossible if it were actually only using the rest mass energy. Now, in this work, we studied how the launching the jet would torque the black hole itself. And we studied this in terms of what's called this dimensionless spin-up parameter, shown here on the top right. S is given by dAdt over times m over m dot. And I like to think of it rather as the rate of change of the spin relative to the rate of change of natural log of the mass. You can see our results on the bottom left here. The spin-up parameter for a thin disk is given by that dashed line, and it's always positive, trying to force the black hole spin up to its maximum value. In contrast, in these GRMHD simulations, all of which were MAD, you get this line that we fit with this fifth degree polynomial, very similar to the solution from this earlier work from Tchaikovsky, if you've been using that in your simulations. And what you see is that the spin up parameter has flipped sign, meaning that in prograde cases, it's clearly spinning the black hole down, and in fact, at a pretty large magnitude. And so you can work out what consequences this may have cosmologically, and that's what we did here on the right here. So this is a simple setup where you initialize a black hole with a particular initial spin and then let it grow at, in this case, this Eddington ratio for 1 billion years. And these two are just degenerate, so one could scale as you like. The point is that if you start off with a black hole that is spinning at that has a spin parameter of 0.9, after a billion years at this Eddington ratio, even if it's accreting prograde, it will spin down to a value of 0.5. And this may have some implications for black holes that need to keep their clusters from overcooling for billions of years, maintenance mode AGN. But perhaps more excitingly, the same physics can hold in the super Eddington regime. In a more recent work that I led over the summer, we take the ansatz, what if all thick disks are mad? Here, all of the evolutionary timescale scale inversely proportionally to the Eddington rate. And so here, the spin down can happen much more rapidly. And nonstop super Eddington accretion is often invoked to explain the assembly of these very massive AGN from seed masses in the very early universe. And so this may be applicable to this kind of situation. So in this case, we looked at super Eddington accretion with 38 different radiative simulations. These explored two different masses, which correspond to fiducial light and heavy seed masses, so 10 and 10 to the 4, a variety of spins, and a variety of Eddington ratios. And in fact, we go down to an Eddington ratio of 0.4 and still see evidence of this spin down effect, which is to say that even if your simulation doesn't actually have super Eddington growth, for black holes that are approaching Eddington, this may also be interesting to you. Each of these is simulating a pi/2 wedge in azimuth just to save computational time. And we know that they're mad when they've saturated in their magnetic flux parameter. And oftentimes we'll see again these cavities caused by a magnetic flux eruption event. So what do we get in this case? Here again is a plot of the spin-up parameter as a function of spin. And now we have another parameter, which is the Eddington ratio, encoded as the colors. On the top, we're calculating the torques directly from the GRMHD simulations. And you can see that as you increase the Eddington ratio, moving from blue to red, focusing particularly on these prograde points over here, you move from the thin disk solution towards the curve that we had from the previous work for MAD GRMHD. The main physics here is that a higher Eddington ratio is able to confine stronger magnetic fields onto the horizon. This powers stronger jets. So we have corresponding equations for the jet efficiency as well. And the stronger jets are going to torque down the black hole more rapidly. We actually developed spin evolution formulae, as well as for the magnetic flux parameter and the efficiency that will apply to all Eddington ratios. I didn't want to get into the details of that in this setting, but we could chat about that if you like. And these are ready to use in all cosmological models if you so desire, which can be an extension to the Chekhov-Skory equations that that some people have been using only for low Eddington ratios. Now in the model, things are smoothed out, of course, and I've pointed out a couple interesting curves. So first of all, Eddington ratio of 1 is shown by this blue curve here. And it's similar, but not quite the same as the thin disk, which is this dotted line. What's really interesting is that the point where it reaches 0 is equilibrium. And we find that with an Eddington ratio of 1, the equilibrium is not at 1, but rather at 0.8. And so this can already start to have effects at Eddington and slightly sub-Eddington accretion rates. Meanwhile, as you go to an Eddington ratio of infinity, you get something that is very similar to the pure GRMHD case, where the Eddington ratio is close to 0. Taking a closer look at this, here's the equilibrium spin as a function of accretion rate. And on top, I'm plotting I'm marking the saltpeter time divided by the Eddington ratio. So basically the characteristic time scale over which you would need to be accreting at that rate in order to start to reach equilibrium. We have these 3 accretion regimes: hot accretion at very low Eddington rates, and then thin disk, and then super Eddington beyond that. So we find that the equilibrium spin is decreasing slowly with the Eddington ratio, again, already 0.8 at an Eddington ratio of 1. And we set things up so that as you move towards a lower Eddington ratio, things converge to a thin disk solution. Now, one thing that we need more work on is this cliff here, which is not real. In reality, this transition ought to be smooth, but this simply has to be studied with radiative simulations on the opposite end, and this just hasn't been done yet. So a few consequences of this. As I mentioned before, the most massive black holes in the universe may have spun down by the BZ effect, and this would be nice to model in a cosmological context. Spin down may also cause super Eddington seeds in the early universe to be at near zero spin. And maybe that'll help reduce their radiative efficiencies. Although at the same time, these are going to be powering strong jets. Not clear what'll win out in that case. And then another interesting point is that the accretion duty cycle is going to matter. It makes a difference if you are accreting 10% of the time at 10 Eddington, where the equilibrium spin is here, versus 100% of the time at 1 Eddington, where the equilibrium spin is up here. So in conclusion, the Event Horizon Telescope is preferring magnetically arrested disks, MADS, which power very efficient jets via spin extraction. The resulting spin down can have an impact on the spins of black holes that accrete at low Eddington rates for billions of years, such as maintenance mode AGN. And the same physics will also hold for super Eddington MADS as well, but much faster, which could be relevant for the growth of seeds. The formulae are easy to implement in your cosmological model if you like, and that you could download the paper here. I also included a helpful Python script that has all of the recipes already encoded, if you like. So thank you, and I'm happy to take questions.
Questions? Yes.
Thank you. This is lovely, and it's been something that we've been waiting for years, so it's really amazing. So something that we found when we tried to implement an earlier version of this in not a cosmological simulation, but a simulation of an idealized galaxy with super Eddington feedback, was that the feedback was limiting severely the time spent in a super Eddington phase. So the equilibrium value is not the one that you predict from the equations, but it's something a bit higher. And I think perhaps Alessandro will also show something on Thursday. Yes. So, do you, we failed completely to find an analytical way of including agent feedback. So my question to you is, do you think that you can include some sort of fake duty cycle in your simulations to see how this depends on effects that are not technically included self-consistently in the GRMHD simulations? If this is a bit too much speculative, just let me know.
So I think what I was thinking of when I brought up the duty cycle here was that, maybe one would assume that if your cosmological simulation with a big time step says that on average it is accreting at Eddington, it's possible to partition that as 10% of the time being at 10 Eddington. I don't have a physically motivated way in terms of the right way to do that. And the assumption here would be that the time scale over which the time scale over which the accretion disk is able to adapt to the new Eddington ratio is small compared to the chunks of time that it's actually turned on and off. Yeah, I'm not sure I have better ideas than that. We could talk more if you like.
Any other questions?
I guess the assumption here is that everything is mad, or at least even the radiatively efficient thin disk. But quasars are about, what is it, 20%, depending on the luminosity. Fraction of them are radio loud. So is there some other reason they wouldn't be having strong jets, or do you think that this just applies to the radio loud regime?
So first of all, their spins could also be zero for other reasons. So you may not get to these equilibrium spins if, for example, accretion is always coming in at random directions, and then you'll just spin your black hole down to zero. Also, if you're below, I think it was about 0.3 Eddington, you do get a thin disk, which is not really mad. The magnetic flux will go down to a negligible quantity, and we set things up so that you would recover the standard thin disk. And I think that's plausible. At the moment, 0.3 is about the limit where these radiative simulations are able to survive without the disk collapsing, and it remains unknown how low you can go and still have a mad.
Thank you, speaker again. Should move on to the next one.
No, below. This one. No, keep going down. Glines, G-L-I.
Oh, this one.
Yeah.
All right, fabulous. So my name is Forrest Glines. I am a postdoc at Los Alamos National Lab, and I'm presenting our first exascale simulations of magnetized AGN feedback. I'm sort of like halfway in between astrophysics and computer science as part of my postdoc. So I'd like to share a little bit about why and how we've targeted these exascale supercomputers. So in astrophysics in general, we always would like more resolution in our simulations, or to be able to do more simulations. So especially if we're planning to do something like machine learning on our feedback models. And for this, we would want more computational power. Exascale supercomputers, representing the next generation of HPC, can provide that power. And looking at the first exascale supercomputers, they're all using some sort of accelerator, all GPUs. Of the top 10 supercomputers on the top 500, only one, Fugatsu, is using a traditional CPU. By having a simplified architecture, GPUs are more power, cost, and performance efficient. And so it's no surprise that all the exascale supercomputers are using GPUs. However, each of the different manufacturers are using different vendor languages from these traditional CPUs, which means that we need to rewrite our code potentially for every new architecture. For example, this is a simple just vector multiply and add for two different GPUs and CPUs. This is not feasible for doing science. Like, we don't want to rewrite our codes all the time. It wastes our valuable person hours of scientists and developers. Fortunately, there are these things called performance portability frameworks that have been implemented that allow us to write our code once, and the framework handles moving it to GPUs and CPUs. This gives near native performance of the GPU languages or the OpenMP. And in the end, it allows us to do faster science in that the code is faster, and we don't have to spend as much time developing and maintaining 3 different versions of the code. All right, see, computer science over. So, in the interest of enabling astrophysics for exascale supercomputers, we developed an AMR framework called Parthenon. It's a collaboration with Los Alamos and a couple of institutions in academia. This is an AMR framework based on Athena++, Athena++'s methods using Cocos, and there are a number of downstream codes that already use Parthenon, including Karma, which was already in one of the talks today. There's also Phoebus, another GRMHD code, Riot, which is a private Los Alamos code. And today, Athena PK, which is our exascale magnetohydrodynamics code, which we've used for cloud and wind simulations, turbulence, and now today, cluster simulations with AGN. So since everyone is giving their big simulation some snappy name with a really awkward acronym, today, just yesterday, we dubbed our simulations X-Magnet. So these are the exascale simulations of magnetized AGN feedback and energetics with turbulence. So this is a suite of isolated galaxy cluster and group simulations. It looks pretty similar to the setup that Trung Ha showed yesterday, in that we have a static gravitational potential. There's some initial perturbations. We have AGN feedback, which is triggered by cold gas. The big draw of these simulations is that we're putting on a little bit bigger than a 2000 cube grid on the inner 200 kiloparsecs. So each grid cell is about 100 parsecs big. The goal of this is so that we can study turbulence and how the AGN feedback thermalizes and deposits energy into the medium. And by the way, this is with magnetic fields, also looking at how the kinetic and the magnetic energy is going to exchange with each other. This is enabled by an Insight Award that we have, which is, they gave us a bunch of node hours on Frontier, which is the first exascale supercomputer. Each of the simulations are 10 billion cells, about that big. Okay, so this is the first simulation. Only one of the simulations have been complete. The rest of the first year are finishing up, but here's a movie. I saw this on Sunday. So, these are, the lines are magnetic fields with some initial perturbations you can see. Here, the jet turns on. The orange is the jet material. It starts out as these polar outflows. Eventually, cold blobs of gas will start to appear, and you'll see filaments start to form where, there they go, these filaments. So what it looks like to us is that these cold blobs are being dragged down these filaments along magnetic field lines, kind of like a bead falling down a thread. We're interested whether this will provide some observational comparisons to our simulations to determine whether, is this feasible, is this reasonable, or does this not look like a realistic simulation? By the way, there's no precession in these simulations. We started to go with a simple feedback model to start with. So the jets are being deflected by the cold gas that's falling into the AGN. So, next slide. Okay, so here's a little snapshot where you can see these cold gas filaments, where along the blue, where the cold gas is falling inward. Yes. Next. Oh, yeah. So here in this movie, we're going to see on the right-hand side is the AGN power and the total cold gas in the simulation as it's going along. On the right-hand side, we're going to see mass density plots. So mass number entry dot plots for entropy and plasma beta. So we can see that the simulation is self-regulating its feedback, which we do expect from how we set up these simulations. So you can see how the AGN power is sort of trailing behind the formation of cold gas, and when a bump goes up, the AGN cold gas, depletes. These mass density plots on the right, you can see this population of cold gas in the center, but as you might see in other simulations. Interesting thing though about our plasma beta is that it's getting near unity or below unity in our simulations. Now, most of the initial magnetic field, most of the feedback is not going into the magnetic fields. We're only depositing 1% of the energy into it. So this is something that we'll need to explore about where is this magnetic field coming from? Is it from the injection, or is it from magnetic fields from the initial perturbations being dragged into the center of the cluster? So there's a lot of stuff that we'll need to look at, a lot of observational comparisons we'll need to make. This is just simulations finished, one simulation finished. The big piece of analysis, oh, and here's also, here's a Flatiron jet. This movie was made by Michael Sandoval very graciously from Oak Ridge National Lab. So you can see plumes of Aegean material. The green lines are the magnetic fields again. So the big peak, come on, next slide, let's go. Oh, there we go. Okay, so the big piece of analysis that we want to do is called an energy transfer analysis. So this is if you break up the energy reservoirs of the kinetic and the magnetic energy along different scales, and then look at how the sum of energies from different scales, how they can contribute to those length scales. You can look at how the kinetic motions transfer energy within itself via advection and compression from large scales to small scales, also within the magnetic fields, and also how the kinetic flows and the magnetic fields transfer energy between themselves, between each other via magnetic tension and pressure. And you can look at how do these kinetic jets actually drive magnetic fields? How does it deposit thermal energy into the medium? And what sort of turbulent spectra do we develop? Does it match Kolmogorov, or is it more similar to magnetized turbulence simulations where the spectrum is different? So this is a piece of analysis that is upcoming that we'll do next year. So sort of our next steps, let this go. The next steps is finish the current set of simulations. So far, this is just a Perseus cluster with a strong magnetic field, about 1 microgauss average. But we have weaker magnetic field simulations, hydrodynamic simulations. We're doing a 10 to the 15 solar mass, larger cluster. We're doing groups. So those simulations are wrapping up this year. Our allocation has also been renewed with more node hours on Frontier, where we'll be exploring anisotropic diffusion, thermal conduction along the B fields. We're also going to implement cosmic ray transport, and I'll be looking at putting in a relativistic speed for the jet, see how that changes things. Yeah, any questions?
Thanks for a nice talk. For the last point in your future stuffs, when you add relativistic speed for your jet, is that a problem? Like, does your time step become too small for your simulation to run, or do you have any like prescriptions for?
So the plan is so these current simulations actually do have a velocity speed limit that we had to put on it to keep the time step controlled. In the relativistic ones, special relativistic, not general relativistic, we will probably only simulate a portion of the simulation. Either a smaller domain, but probably a smaller time length. Like this is a few cycles of the AGN, we're gonna simulate one.
Also, I had another question, if that's okay.
Yeah.
I was just curious how you actually like put in feedback in this simulation, because it's not coming from like full GR.
No, it's
so
not.
I was just curious.
So it's a prescription model. In the end, we do have to cheat somewhere. So we are putting in a thermal heating thing. It's within, I think, half a parsec. Yeah, it's a few cells. There's 2 jet outflows that we start on either side of this, and some magnetic field loops that we also insert in the same region. So if you zoom in, you can see where we're cheating, but it's just a prescription model.
Thank you.
Yeah.
Yeah, how are you
I may have missed this. How are you actually feeding it? Because you said that the cold gas mass is changing and that's changing the power. So they're linked somehow.
Oh, yeah. So in our prescription model, this is following like Debrat Prasad's, how he was approaching things. There is a accretion zone where we deplete the cold gas within that zone. It's I think it's 1 kiloparsec in radius. So it's a few, I think it's smaller. I think it's half a kiloparsec in radius. So it's just a few cells at the center of the simulation that we deplete the gas.
And it's just on like a free fall time scale or something.
It is on a 10 million year. Yeah.
But do you have mesh refinement or in the central region if you want to get some high resolution or?
Oh, yeah. So in these simulations, we did not do adaptive mesh refinement. And particularly it's because doing a magnetic feedback model like this with adaptive mesh refinement could introduce a lot of artifacts. Also, by not doing adaptive mesh refinement, we avoid a lot of load balancing problems. Yeah, we're sort of picking the problem that we can do well.
Thank you.
Thank you.
This is yours, right?
Yep.
All right. Hi, everybody. Thanks for being here. I want to talk a little bit more about this problem that we have in implementing black hole physics in galaxy scale simulations and how the amount of flexibility we have in those choices can be sort of problematic in how we interpret the outcomes of those simulations. So fortunately, a lot of my introductory slides have already been covered. So I'm just going to say one sentence per slide here. People do cool GRMHD simulations. We can't do them in galaxy formation simulations because they're too small. But we need to do something because if we don't do something, we don't get red massive galaxies. Right? So one way to look at that is with the stellar mass halo mass relation shown here, which tells you the efficiency with which gas is being turned into stars as a function of halo mass. There's that characteristic turnover at halo masses of 10 to the 12 and above. And the standard Fire2 simulations, these are zoom-in cosmological simulations of galaxy formation that do not include any black hole physics, match this relation as well as many others up to a halo mass of 10 to the 12 and then systematically overshoot it, indicating that star formation is not being regulated enough in those galaxies. And if we look at the star formation rates in the same galaxies, this is the star formation rate at the final snapshot relative to the star forming sequence. You can see that all of the galaxies, regardless of halo mass, are more or less lying along the star forming sequence, including the most massive ones, which we know ought to be quenching. And if we look at the actual galaxies themselves, you can see an image there of the gas temperature and density, with blue being cold and pink being hot, and then the corresponding stellar light on the right. At all masses, you end up with a little bit of a star-forming disk, even at the most massive end, even when a hot halo is formed, in the absence of including any AGN physics. So, but of course, the problem, as we know, is that we can only describe what's happening on the scales that we can resolve. We have to try to say how inflows are happening from the scale we can resolve into the black hole accretion disk system where all this complicated stuff is happening. And we have to describe the emergent outflows at the scale we can resolve. And so there are a lot of choices that we can make in exactly how to model that. And many different simulation collaborations make different choices, which are all quite physically reasonable. So we have to have some model that describes how mass gets from the resolvable scale into the accretion disk system. We have to normalize that model according to some accretion efficiency. Those two things are kind of a priori unknown and maybe resolution dependent. We have to model how the mass gets from the accretion disk onto the black hole itself. Maybe the most straightforward part, let's just call it an alpha disk. And then there is various forms of the feedback that have been described that can manifest at the resolvable scale in a number of different ways, either as radiative feedback with radiation pressure parameterized by some efficiency that describes the momentum boost, mechanical feedback in the form of physical winds, which are launched from the disk with some velocity, which is unknown at that scale we can resolve. And also feedback from cosmic rays, which are generated with some unknown efficiency. And then on top of that, we have to choose exactly how we're going to put this mass and energy and momentum back into the simulation. Do we just put it into the surrounding resolution elements directly? Do we push them, kick them? Do we spawn new resolution elements and let them go off into the universe? And should it really be isotropic or should it be collimated? Because we know that AGN launched these highly collimated relativistic jets. And everything I've circled here in a red box is something where we don't necessarily know what the quote unquote right answer is because we can't do this physics from first principles. And so we have a lot of flexibility within this space. And there are a lot of really reasonable choices that can be made here. And what I was interested in thinking about was, given all this flexibility, how can we most reasonably implement this physics in zoom-in simulations of galaxy formation? Or if we kind of turn the question around, given all of that flexibility, what are the physical properties of the black hole models that can produce quote unquote good quenching behavior in galaxy populations? Not looking for the correct quote unquote model, but looking for the properties of models that lead to nice galaxy outcomes. And there's a few different ways that I'm going to characterize whether something is good, mostly by whether they can land on well-known scaling relations, like the stellar mass halo mass relation that tells us about the regulation of the galaxy growth, the M sigma relation, which tells us about the relative growth of the galaxy and the black hole, and the star formation rate, which tells us whether the galaxy has been quenched or whether it's actively star forming. And we ran a big suite of simulations, all zoom-in simulations from the dwarf galaxy mass up to the massive galaxy scale, which explored this parameter space that I told you about in the previous slide. So we tried several different accretion models, although we narrowed it into the most reasonable ones to start with. Explored accretion efficiencies and various values of these forms of feedback. I'm, for brevity's sake, going to wrap that into a single eta feedback, although there are, of course, differences between the different channels. And as Kuni alluded to earlier, we do kind of find that cosmic ray feedback tends to be the most effective. And a lot of our most well-behaved models are, in fact, dominated by the cosmic ray feedback. But you can achieve quenching with these other mechanisms as well. And then we messed with exactly how we are implementing the feedback. Here are some of the details for those of you who are interested. You can see the resolution there. It's low by fire standards, but still somewhat high compared to other simulations, which are larger in volume. We focused our efforts on 3 halos in particular, one at the massive galaxy and one Milky Way mass, one dwarf galaxy, and then ran some models on other halos as well. And there's about 500 runs in total, spanning all that big parameter space. And if we take all 500 simulations and plot them on these 3 relations, here's where they end up. Really all over the place because we spanned a lot of different possibilities in how we want to model the black holes. It is entirely possible, of course, to move massive galaxies down onto the correct relation and quench them. It's also extremely easy to just completely kill the dwarf galaxies and knock them down off the relation as well. So the question is, how does the outcome of the simulation depend on the combination of modeling factors that I just described? And I'll show you a few examples that I think illustrate what's going on here, some of the trends within the suite. Here, points which are the same color, use the same black hole physics, but have different initial conditions. They're different halos. And here's what those three galaxies, dwarf, Milky Way, massive galaxy, look like without any AGN. If we look at this blue model up here, this is an example where despite AGN physics being included, there appears to be no effect on quenching the galaxy. You can see what those galaxies look like. And this model surprisingly actually has fairly strong feedback. I'll put the parameters up here, but I'll characterize it for you qualitatively. This model has pretty strong feedback in all channels, but a relatively low accretion efficiency. And it doesn't manage to quench any galaxy at any mass. If we move to the orange model here, we're cooking with gas now. We have managed to quench the massive galaxy, move it down onto the stellar mass halo mass relation, and the other two look more or less undamaged. So that's good. Well, I mean, the Milky Way's got a hole in it, but that's okay. And this one also has pretty strong feedback, relatively strong. The main difference between this and the previous one is that it has a higher accretion efficiency compared to the other one. And we managed to quench massive galaxies. That's great. We also commonly see over-enthusiastic black hole models, which over-quench dwarf galaxies. This particular model actually has weaker feedback in all three of those channels, but a relatively high accretion efficiency. And then, of course, there are some models that really just destroy everybody. I'm not even going to show you any pictures because it's just black squares. This model has really strong feedback in all channels and a very high accretion efficiency. So from these examples, you can already start to glean some of the trends that exist within this data set. The first is that the regulation of star formation is closely related to the self-regulation of the black hole growth. On this plot, I'm showing star formation or stellar mass relative to the stellar mass halo mass relation. So how well regulated the stellar mass is against black hole mass relative to m sigma, how well regulated the black hole mass is. If I put all of the simulations on this plot, it looks something like this, where fortunately in the middle here, near 1, 1, are simulations where both the black hole and stellar mass growth are well regulated. But there are also plenty of simulations with over massive galaxies and under massive black holes, and lots of under massive galaxies with over massive black holes. And so this kind of tells us a story where the more the black hole accretes, the larger it grows, the more feedback energy it puts into the environment, and the more the galaxy quenches. But of course, it's complicated. There's a lot of scatter in this. And we can break this down a little bit more. So how do we achieve appropriate black hole growth? So it turns out, of course, to be complicated, depends on both the accretion and feedback efficiencies, and seems to be halo mass dependent, unfortunately, where for the most massive systems, if we look at black hole mass relative to m sigma as a function of the accretion efficiency in the model, models with higher accretion efficiency lead to more massive black holes, which makes sense. But if we look at the lower mass systems, particularly in the dwarf galaxy regime, that trend kind of goes away and is replaced by a color gradient, where the color indicates the feedback efficiency, where models with stronger feedback are more self-regulating the black hole and stopping it from growing. So depending on which end of the mass spectrum you are, you can have a stronger effect from changing the accretion efficiency versus the feedback efficiency. Then let's say that we manage to get the black hole to be a nice mass. How do we then try to regulate the star formation? Well, it depends, of course, on the total amount of energy released in feedback, but not only that. For dwarf galaxies here, you can see stellar mass relative to stellar mass halo mass as a function of the total amount of black hole feedback energy that's been released relative to the binding energy of the halo, as Tiago said something about this morning. And for dwarf galaxies, once you pass the binding energy of the halo, you start overquenching it. But for more massive galaxies, again, it becomes more complicated again, but that's neither necessary nor sufficient to quench a massive galaxy. You can give it more energy and not quench it. You can give it less energy and overquench it. And here that seems to be related to something I'm calling responsiveness, which is the product of the accretion and feedback efficiencies, which determines it's related to burstiness, where if the feedback is produced more gradually, it's less likely to quench the galaxy. If it's produced in strong bursts, it's more likely to quench or overquench. Okay, and then very quickly, I'll say, obviously, it's very complicated to achieve nice quenching behavior across many halo masses. There's a lot of balances that you have to achieve here. There are actually several models within the suite which are able to do it. They can have very different parameterizations, but they manage to kind of satisfy all these balances. And maybe this is an indication that feedback should be a function of halo mass, I don't know, but it does kind of say that there is no quote unquote correct way to model it necessarily, at least according to these very broad parameters. And there's a lot more kind of details for us to dig into in this suite. And I think I'll just leave you there with my summary. Thank you.
Hi, great talk. So in the plot where you showed the normalized M star versus normalized M black hole, you focused on overmassive galaxies and undermassive black holes and vice versa. So there are a few systems where both the galaxy and the black hole are either overmassive or undermassive. So what's going on there?
You were talking about the quadrants where I haven't put circles. There are a couple, but they're pretty close to the middle there. So I would say you could have a case where the black hole gets overmassive, but it's like super, super wimpy feedback. So it doesn't manage to overquench the galaxy. So you can kind of push these relationships a little bit. Yeah.
Thank you.
That's a great talk. So when you're modeling radiative feedback and cosmic ray feedback, how are you distinguishing it in these galaxy scale simulations? Is it just different feedback efficiencies, or there's something more?
Oh, the cosmic rays are modeled as like a separate parallel fluid, whereas the radiative feedback is like a pressure that is imposed on the surrounding gas. So they're numerically distinct.
I see. Thank you.
Yeah.
Thank you. We should move on. Our last speaker is remote. I see it's already online. You share your screen.
How does that look?
Okay. It was great. Yeah.
Great.
Go ahead.
All right. Well, thank you very much. And I apologize that I can't be there in person. This has been a very interesting meeting to sort of dip into remotely. And I do appreciate that I have the coveted last talk before lunch, so I'll try to keep things pithy. Fortunately, a lot of what I was going to say has already been talked about by various people, so I'll sort of focus on the things that haven't been discussed. All right, so the first point I want to make is it's clear that galaxies of all masses regulate themselves. This is a pretty famous plot at this point from Baruzzi, Wexler, and Conroy. What it's showing is the stellar mass fraction, so the mass of stars compared to the virial mass or the total mass of the halo as a function of halo mass. And this is synthesizing a ton of different surveys. And so what it's showing is the redshift evolution from redshift 8, which is pretty early on in the universe, to redshift 0, which is this black line of the galaxy distributions in terms of the stellar fractions. So in other words, what fraction of all the baryons could be turned into stars. And the error bars are showing you the standard deviation. And so it's showing that this, not only does this behavior vary as a function of halo mass, it also seems to be a relatively tight relationship, even though there is some dispersion, as others have mentioned. And so our current understanding of this is that at relatively low masses, this is mostly due to stellar feedback, so supernovae. But at higher masses, and in particular, really massive galaxies, it's mostly due to, the behavior is mostly due to AGN feedback. And quenching, of course, in massive galaxies is primarily understood to be AGN feedback driven. And so I'm going to be focusing on the right-hand side of this plot today. And so we've been talking a lot about the supermassive black holes and feedback from them, but I want to focus on the physically larger scales. And I just want to make another observation, which is all galaxies have a hot atmosphere. And so galaxies like the Milky Way have a circumgalactic medium where if you sort of add up all of the diffuse plasma that is outside of the disk of the galaxy, but within the virial radius, it's about half of the mass of the baryons in the entire system. And so, stars plus ISM are about 50%, CGM is about 50%. And as we go to larger galaxies, we see that that is true as well, and the fraction grows. And so there's this large reservoir of circumgalactic plasma, or intra-group plasma or intra-cluster plasma, sort of depending on the physical scale that you're thinking about. And this is something that's relatively easy to ignore, but it's extremely important. And we want to understand what role the CGM plays, because there is that implication from the previous slide that there is something that is tightly regulating the evolution of the stellar component of the galaxy. And a lot of theory has sort of suggested that the CGM or intergroup medium, et cetera, is important for that. And so what I want to do is talk about some work that we've done to try to understand how the CGM and supermassive black hole feedback interact with each other. And of course, we know that they do. This is a picture from, it's a multi-wavelength photo or an image of a galaxy cluster. So the serial number of it is written up there on the left. And the key point that I want to make here is that in this galaxy cluster, we see tons and tons of X-ray emission. There is a central elliptical galaxy that you can see in visible light. And then there are these relativistic jets that are definitely coming from the supermassive black hole. And so, but the jets go out to, many kiloparsecs and, hundreds of kiloparsecs. And so, and there's a lot of evidence at the galaxy cluster scale that these systems are self-regulating. The gas at the center that is emitting X-ray radiation like crazy has cooling times that are substantially less than a Hubble time, so tens of millions of years, or maybe hundreds of millions of years. And so, but we never see clusters, or almost never see clusters, having huge starbursts in those central galaxies. And we never see them exploding. And so there's some sort of thermostat-like mechanism at the galaxy cluster scale, at least, that's doing this. And then we also see it at the group scale. And so this is just an image from a group. And what you're looking at on the left is the X-ray image. On the right, it's the, it's an optical image. And what we're seeing is, X-ray cavities that are, that are coming from multiple AGN outbursts. And then, you just don't see it in the optical image. But the main point here is the AGN, is providing a lot of feedback on the circumgalactic gas that is doing something to it. And we really want to understand the details of that. And unlike some of the previous work, I'm going to really focus on idealized simulations here, because, well, quite frankly, there's a rich history of simulating AGN feedback in idealized groups and clusters. And so there are folks that are related to various names that are on this list. But in general, these are really useful experimental setups, like these idealized simulations are very useful experimental setups for trying to understand causality, right? You can have a very simple setup and you can understand for an AGN jet, AGN feeding prescription and jet prescription, or feedback prescription, I should say, what exactly is happening. And so I'm not going to run through this entire list, but over the last sort of 15 years or so, 12, 15 years, there has been a sequence of work from a bunch of different groups that has shown that in these galaxies and groups now, we see that the central gas can produce the central higher density gas produces cold gas, multi-phase gas, that can feed the galaxy, the supermassive black hole, and then feedback from that supermassive black hole in turn heats up the intergalactic, intercluster, or circumgalactic medium, and then we see that this regulates itself over time. And so there's a lot of really, really nice work that's gone into this. And we've been really working to try to understand why. And I've been collaborating with Mark Voigt, as is Greg Bryan and possibly other people in the room. I'm actually not sure who's physically there. And one of the really nice pieces of work that has come out of this collaboration has been this work that Mark Voigt led on black hole feedback in massive galaxies. And I want to emphasize that this is just sort of looking at massive galaxies, but it applies to thinking about galactic systems in general. And so one of the important observations that was made was that when you look at galaxies that are quenched, the stellar mass of the galaxy is a pretty noisy indicator of quenching. What is more closely related to that is the central velocity dispersion. So the velocity dispersion of the stars at the center of the galaxy. And what that implies is that, if you have a higher velocity dispersion, that central potential well is deeper. So this is sort of going back to physics 1, right? And the idea being, the hypothesis was that if you have a deeper potential well in the center of your galaxy, it is going to more efficiently move gas onto the black hole, or push gas to the black hole, I suppose, and it will make your AGN more efficient. It will cause a more energetic AGN outbursts. And so the other, one of the things that was postulated in this analytic work was that the AGN jets primarily lift the CGM. So instead of thinking about just making the CGM hotter in general, what that energy is doing is ultimately causing the CGM to be lifted up. So moved upwards in the potential well, further away from the center of the galaxy. And one consequence of that is it lowers the pressure of the CGM and allows supernova feedback. So, in massive galaxies, we're talking primarily about type 1a feedback, to derive galactic outflows, and that can sweep gas out of the galaxy and essentially remove gas that would otherwise be feeding a supermassive black hole. And so, and then in really massive galaxies, that's going to quench. In less massive galaxies, that's going to cause circulation and multi-phase gas formation. And then the central potential and also sort of how gas is distributed impacts this behavior. And here's the best analogy that I can come up with for this. So the way to think about it is the gas acts like a lid sitting on top, or the CGM acts like a lid sitting on top of the galaxy and regulating what's going on. So we can test this numerically. And I'm going to actually, I'm just going to go through this. So what we do is we use the ENSO adaptive mesh code to do simulations of AGN feedback in 2 different galaxy groups, representing the extremes of this analytic prediction. And so one has a very deep central potential well and a steep entropy profile. That should say entropy, not entropy, my bad. And what that means is a steep entropy profile means that the density of the gas falls off very, very rapidly. So your CGM is very broadly distributed already. There just isn't a lot of mass in the CGM close to the galaxy. And then a second simulation of a galaxy with a similar mass, but a shallower potential well and a shallower entropy profile, I should say. And what that means is you expect there to be a lot more gas close by to the galaxy, and thus available to feed the supermassive black hole. How much time do I have left, by the way?
2 more minutes.
4 minutes? Okay, great. I'm sorry, I didn't mean to make it 2 minutes, you said?
2 more minutes, yes.
All right, then I'm going to have to be very fast. So just to give you a sense of what's going on here, this is one of the two simulations where we have a very steep entropy profile. And so what's happening is, let me rerun this. What you're seeing is the AGN actually doesn't do a whole lot. The density of the CGM is very low. Gas does not cool very efficiently. What gas there is that cools efficiently is right at the center of the galaxy. And so it causes the AGN to occasionally go on and deposit its energy out at, tens of kpc. But the galaxy, the AGN does not actually need to inject a lot of energy to do much. And then if we have a galaxy, and so this is the same color scale, same physical size, but this is that galaxy that I was talking about that has a shallower entropy profile, so a lot more gas around to feed the galaxy, to feed the black hole. And what we're seeing is, a much more active supermassive black hole. Looking at this more quantitatively, I appreciate I don't have a ton of time to get into it, but this bottom, let's cut off. Anyway, the bottom row here is essentially the AGN jet compared to the supernova power. And the thing to take away from this is you get a big burst of AGN energy in this sort of shallow, the low central density, steep entropy profile one. And then it just sort of percolates along doing very little. And what ends up happening is the supernovae, the very few type 1A supernovae that are going off in there, provide enough energy to sort of push the gas out and keep this whole system regulated when the potential well is steep and the entropy profile is steep and there's not a lot of gas around. So the lid is very light on our pressure cooker. Whereas if you have a more extreme situation where there's a lot of mass and you allow the gas to cool off relatively easily, then for the same axes, what you see is the AGN is just much more active and the supernovae just never really are that important. And then the big takeaway from here is what I was that these simulations back up this analytic work, that the AGN really rearranges the circumgalactic medium. And don't worry about all the words, but the key point is that we saw in these simulations, AGN feedback takes the gas in the CGM and moves it outwards. And what that does is it reduces the density of gas in the center of the galaxy, and drops the AGN feedback. And so we see evidence that there is this thermostat-like regulation mechanism. And then Forrest already talked about our self-regulated exascale simulations. So I was not planning on talking those, even though I am out of time. So, okay, so what are the key takeaways? So first off, supermassive black holes are really tightly coupled to the galaxies in which they live. What we have come to understand from work done by a lot of groups is that interplay between the gravitational potential of the system, so not just the virial mass, but how exactly the matter is distributed, the distribution of gas in the circumgalactic medium, or the intergroup medium or intercluster medium, depending on the scale that you're looking at, and the behavior of the supermassive black hole, so its feedback and its growth, are really crucial. So there's this sort of thermostat-like mechanism that depends on all of those things. And what we have also found is that the supermassive black hole consumes the dense gas around it, deposits energy at very large radii, many kiloparsecs, and this energy ultimately goes into raising the gas up in the potential well and reducing the density of the gas sort of at the center of the galaxy, rather than primarily heating it up. So you're taking gas, and obviously you're putting heat into it, but the net result is that rather than just making everything hotter, you're physically putting a lot of that energy into raising it up in your potential well. And finally, I wanted to note that the simulated behavior that we see largely agrees with our analytic models, though a lot of details still need to be understood. And also, it's worth noting these simulations are not resolving down to the scales that some of the folks earlier this morning have talked about. So thank you very much.
Thank you. We still have time maybe for a few questions if you're not too hungry for the lunch.
So I cannot see the audience, just FYI.
Hi, Brian. It's Jake Bennett here. Really nice talk. I was wondering, because the analytic kind of argument is talking about lifting the whole CGM, but at least in the simulation you've shown so far, and I guess I don't know how much jets shift, but you're dumping energy at a distance in a preferred direction. Does that affect the amount of lifting that actually happens, or do you only lift in a certain area, or does the cluster weather kind of distribute it a bit more?
Right. So what we see in in the simulations that I share or that I showed movies of, what we see is there's quite a bit of circulation that is driven by the AGN, right? So you're lifting the gas, or the jets are sort of bipolar, but you do see circulation coming back down to the equatorial plane, and you see the lifting occurring everywhere. And so I think the cluster weather, I guess, for lack of a better term, as you were saying, does tend to cause that energy to be distributed around. And so it's not just in the directions of the jet.
Okay, thank you.
Yeah, thanks.